Hey, so welcome to another week of Physics 30. This week we are going to look at diffraction, which is the last week in light's waviness. After this week, we're going to look at some particle properties of light. But in Physics 20, we looked at how waves act when they strike an opening. So if we have waves, so these waves are coming in, they're straight waves, they hit this barrier. Waves spread out like they're coming from a circular source. So they will spread out and fill in the space behind that opening. So waves hitting a barrier with an opening, they diffract. We call that diffraction when they go around it. So waves will diffract the most when the opening is close in size to the wavelength. So the closer the opening is in size to the wavelength, the more diffraction will occur. Now, one special property of diffraction is interference. And so we're going to look at kind of how that happens. When it comes to diffraction itself, Huygens explained it as wavelets. So he kind of looked at diffraction as saying, like, at each point there's these individual sources of waves. So when they go past the obstacle, these wavelets meet and overlap each other, forming the new wavefront with no gaps. So he used the principle of wavelets in order to explain it, kind of like bubbles in a pond. Now, for diffraction to be observed, the size of the opening needs to be about the size as the wavelength of the wave. Now, this is important when we're looking at light, because light has very short wavelengths relative to things that we observe. So in order to observe diffraction of light, we need very, very small openings. So if a wavelength is much bigger or smaller, diffraction will be difficult. And so this is one of the reasons why it was hard to explain light as a wave, because it took them a while to actually identify that these slits need to be really small in order for diffraction to occur. Now, different wavelengths of light diffract different amounts. Remember, if we look at refraction, so when we looked at refraction, we said red refracts rotten. So that means that red light refracts a small amount, whereas blue light refracts a large amount. For diffraction, that is different. Now it's flipped. So red actually diffracts the most. And shorter wavelengths like blue diffract the least. So it is flipped from refraction. So red refracts the least but diffracts the most, and blue refracts the most but diffracts the least. So it is flipped, and we keep that straight. Now, Young did a double slit experiment which kind of turned the world on its head and really lent a lot of support to light's waviness. I would suggest that you watch the Veritasium video. So he builds a similar experiment and takes it out into public. And there's a very good diagram there of kind of explain, and he has some really good demonstrations of what we're going to talk about in this video. But I would suggest that you kind of go and watch that video to kind of understand more about what was going on in Young's double slit experiment. But basically, he took light and he shot it at a screen with two slits. Now, if light were a particle, we would expect that on the viewing screen, we would see those two lines, right? We would see this light hit these slits. Anything that did not hit the slit would bounce back or be absorbed. Anything that hit the slit would travel through. And on the viewing screen, we would see those two slits. Now, if light were a wave, we would see something different. As light hits these two gaps, a wave would diffract. Now, as it diffracts, then, these waves would appear as they're coming from two sources, and they would interfere with each other. We would have places on the screen where they interfere crest with crest and interfere constructively, and we get a bright spot. And we have places where they would meet up crest to trough, interfere destructively, and we would get a dark spot. So what we would see on the screen is alternating light spot, dark spot, light spot, dark spot, light spot, dark spot. That's called an interference pattern. So that's the observation. If we observe an interference pattern, what we can actually infer from that is that that source is a wave because it's behaving like a wave. So we observe an interference pattern and we infer wave-like behavior. So we see these dark spots where they interfere destructively and these bright spots where they interfere constructively. And so we get a spot in the middle where it's most bright, and then we have dark spots, bright spots, dark spot, bright spot, dark spot. We see this interference pattern. And that was kind of all they needed to be like, oh, okay, light is a wave. We accept that. That's the only way we can see this interference pattern because we know it is a very wave-like thing to actually observe. So here's one way to see diffraction at home. If you take your fingers and make a really small slit and look at a light source, so if you look through the eye, you'll see inside, you'll see alternating dark and light bands. So you can see an interference pattern. You can't really see it on this video, but if you hold it up over your eye and look at a light source, you'll see alternating dark light. It'll look kind of like a fence. That's an interference pattern that you're actually observing. So when we look at this central place, so in this central bright spot, that is kind of where we start from. That's our origin. As we branch out, we get different order fringes. Now remember, light has different wavelengths, and different wavelengths diffract different amounts. So when we get to that first order rainbow, we're going to have blue. That's going to be N1. That's the first order fringe. If we continue on, we'd actually see second order fringes. So then we would end up at red, so the end of that first order rainbow. And then all of a sudden we would have that pattern repeating again. That's the second order rainbow, or N2. Now the first equation we're going to look at is the small angle approximation. And the name is important. It's for small angles. So less than 10 degrees, and this is a relatively accurate way to do this calculation. Anything more than that, and it starts to diverge from the actual answer. But this equation is lambda, so the wavelength, is equal to x, which is the distance from the central fringe. So if in this example, maybe we're going to N2, so x is the distance from the central fringe, times d, the distance between the slits. Now these are all in units of meters, divided by n, so the order of the fringe. So if we're looking at the first one, it's 1. At the second one, it's 2. Times L, which is the length from the screen. So that's lambda is equal to xd over nl. So here we have a question. We have a pair of screens placed 13.7 meters apart. So we have a screen here and a screen here. That's 13.7 meters. We see a third order fringe. So this is n equals 3. And that distance, so from the central fringe, that distance is 2.50 times 10 to the negative 2 meters. The slits, so the distance between these slits is 0.0960 times 10 to the negative 2 meters. And we want to find the wavelength and what color it is. So lambda is xd over nl. So x is my distance to that fringe, so 2.50 times 10 to the negative 2 meters, times d, the distance to the slits, between the slits, 0.0960 times 10 to the negative 2 meters, divided by nl, so n is 3, nl is 13.7 meters, and we can identify what that wavelength will be. So So 2.5 second EE negative 2 times 0.0960 second EE negative 2 divided by 3 divided by 13.7 gives me 5.83 times 10 to the negative 7 meters, or 583 nanometers. Now 750 is red, violet is like 350, so I would think this would maybe be around yellow or yellowish green when it comes to that wavelength and what color it would be. Now, people have used this method before. When they talked about DNA and being a double helix, this was kind of one of the ways that they determined that. So there was some DNA, and with an X-ray, they ended up with this developed film. From that X-ray diffraction, they were able to determine the shape of it and also the relative size. You can also use something like this to measure the width of a hair. Here's the interference pattern produced by a hair. It's kind of hard to see, but there is a first order fringe that's over here after that bright spot where it's spread out. Now you can do this so using a laser pointer at home if you want to know how thick your hair is. I think we would admit that measuring the width of a human hair is quite difficult. However, if you have a laser pointer, you can tape that hair over top, turn on your laser, and then you can produce an interference pattern on the wall. If we know the distance to the wall, so from the wall to the laser, and then also we can measure that distance between those bright spots, the first order fringe and the central bright spot, then we have X, we have L all the way back, and we can use that formula because usually the wavelength is written right on the laser. We can use that formula to find the width of that human hair. The second way to calculate the wavelength, the second diffraction formula is the sine theta formula, d sine theta. Now, if we think about that first method only works when this angle is less than 10 degrees. So if that angle is less than 10 degrees, then we can use lambda is equal to xd over nl if it's smaller than 10 degrees. Now we kind of need to check that anyways. So if we want to check that angle, right, we have L and then this is X. That's where that angle comes from. So my tangent of that angle is my opposite, which is my X, over my adjacent, which is L. That's how we check that angle. So if we are checking that angle here anyways, sometimes it makes sense just to use this d sine theta method. Now in some experiments, using this xd over nl makes more sense because it's easier to graph our responding and manipulated variable. But if we are checking that angle, then just plugging into that d sine theta expression makes sense as well. Here we have a diffraction grating, and we have two different wavelengths of light. So we have red light and we have green light. So we have red light here. So you can see where it diffracts to. If we were to go to green light, so we would be decreasing the wavelength. If we think about our equation, wavelength on the left-hand side goes down, that means the right-hand side needs to go down as well. So the angle should decrease. So if I switch it to green light, now you see that those dots are closer together because it has a smaller angle. So it diffracts less than red light. So red light, green light, different wavelengths diffract different amounts, and the equation supports that. So here's a question using that. So we have yellow light. So we have lambda is equal to d sine theta over n. And we want to find out what angle we need to look away to see the second order fringe So n times lambda over d is sine theta. So I'll just go all the way. So sine to the negative 1 of n times lambda over d is theta. So that's sine to the negative 1 of n. So I want to see the second order fringe. My wavelength is 540 times 10 to the negative 9 meters, it's nanometers, divided by d. So 2.20 times 10 to the negative 6 in order of meters. So I'll put that in my calculator. Sine to the negative 1 of 2 times 540 times 10 to the negative 9 divided by 2.20 times 10 to the negative 6. And I get 29.4 degrees to 36 pixels. So if I have my slits here and my screen here, I would have to look off at an angle of 29.4 degrees to see that second order bright spot. Now, one thing to talk about is diffraction gratings. So having really small slits, as you saw in the one example, is you can create an interference pattern with just one slit with your fingers. However, it's not super clear. So what we can use is what's called the diffraction grating. So they take a whole bunch of lines, and so this happens over and over and over again. And you get a much better image the more lines that you have. Now when it comes to, we can determine, so we do want to know the distance between the slits. To do that, so diffraction gratings are usually numbered, like maybe this is like 550 lines per millimeter. That's usually how they label diffraction grating. So how many lines in a certain unit of measurement? If we want d, the distance between the slits, we need to take the reciprocal of it in units of meters. So if I want to know the distance between the slits, I take my 1 millimeter, so 1 times 10 to the negative 3 meters, divided by how many lines in that millimeter, and then I have my distance between the slits. So sometimes we do need to go from what the diffraction grating is labeled to a unit of measurement for d, and we would do it that way. Here is an example of a diffraction grating with a lot of lines. This is a spectral decoder that came in a Bright Eyes CD, but you can see when you move this over the artwork that it actually causes the artwork to appear. So it's a hidden message. But because there's lots of bands, so there's lots of lines in this diffraction grating, and so it ends up producing a very clear image when you move that spectral decoder over top of it. So here we have a diffraction grating labeled as 600 lines per millimeter. So d would be my 1 millimeter, 1 times 10 to the negative 3 meters, divided by 600 lines in that millimeter. So 1 times 10 to the negative 3 divided by 600 gives me a distance between my slits of 1.67 times 10 to the negative 6 meters. So I want to find the color of light, lambda. Angle from the central band to the first fringe is 17.5. So I have d sine theta over n. D is 1.67 times 10 to the negative 6 meters times the sine of 17.5 degrees divided by 1. So my answer times sine of 17.5 degrees gives me a wavelength of 501 nanometers. So two equations, d sine theta and xd over nl. The xd over nl is a good approximation for small angles. The d sine theta is better for large angles. We can see graphing questions. We can see some simple calculations like this, and also just some relationships between different types of variables when it comes to these diffraction formulas.